Okay, let's get started. We're going to do scientific computing, which means that we want to make models of a physical system and then use numerical analysis to do calculations with those models on a computer and hopefully compare the results to actual experimental data. In order to get started on this project, we need to first understand how computers represent numbers. A floating point representation is simply a decimal number, for example, a number of the form 1.60 times 10 to the minus 19, in which the decimal can float. And so this decimal is called the floating point. Floating point. And of course, the reason why you want to have a floating point is because if this decimal moves back and forth, the computer can represent a much larger range of numbers than it would be able to if it didn't let the decimal point float. Just two more pieces of nomenclature. This is, of course, called the exponent. And this is called the mantissa, and they're stored separately in the computer. All right, before we look at the specific way that modern computers store floating points, let's review decimal and binary notation. If you're already familiar with decimal and binary notation, you can skip forward a couple of slides. Okay, so base 10 or decimal representation, you might represent a number like, for example, the number 256. And of course, this is the ones place, this is the tens place, and this is the hundreds place. Okay, so this number is 2 hundreds plus 5 tens plus 6 ones, and you may already be able to guess why I chose this particular number to represent. The number might have a decimal or a fraction, so you might want to, for example, represent the number 256.125, and again, you might already guess why I chose 0.125 to be my decimal. In any case, this is the tenths place. This is the hundredths place. And this is the thousandths place. So, another way that you can generically write a number like this would be to consider the form where each number has a digit. So for example, you might have D0 dot D1, or you might have a more complicated number like D2, D3. Oop, this is D to the minus 1, D to the minus 2, D to the minus 3. This is D1, this is D2, this is D3. And each of these digits, each possible digit D would be 0, 1, 2, 3, dot, 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 up to 9, dot, 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 up to 9. This would be 1/10, and this would be 1/100th, and this would be 1/1000th. So the reason why we label the digits with the subscript that we do is because it indicates the exponent of the power of 10 that we want to multiply that digit by when we say which power it is. So you could think of this number as being like D3 times 10 to the 3 plus D2 times 10 to the 2 plus etc. Okay, let's talk now about base 2 representation. So in base 2 or binary representation, you might write a number in the form, for example, suppose you had 8 digits to represent your number, and all of those digits were binary digits. So B is going to be a binary digit, and the binary digits are either 0 or 1. And so suppose you have 8 digits. You might write something in the form B5, B4, B3, B2, B1, B0, dot, B minus 1, B minus 2. Oops, I've already represented 9 digits here. Pretend like I erased that one. Okay, so I have 8 binary digits here. And now this is, instead of being the 10 to the minus 1 place, because this is binary, this is the 2 to the minus 1 place. This is the 2 to the minus 2 place. This is the 2 to the minus 3 place. This is the 1's place, or the 2 to the 0 place, etc., all the way up to the 2 to the 4th place. Okay, so suppose that you wanted to represent the number that in decimal was written as 256.125. Well, 256 is equal to 2 to the 8th, and 0.125 is equal to 2 to the minus 3. So let me just indicate here that this is the decimal representation. And now, having figured out the relevant powers of 2, we can easily write the binary representation. And of course, this is the reason why I chose this number to show the decimal representation, because it's a number that can be represented exactly in both decimal representation and binary representation. Because this is 2 to the 8th, we'll put a 1 in the 2 to the 8th place, a 0 in the 2 to the 7th place, a 0 in the 2 to the 6th place, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2, 2 to the 1, and 2 to the 0, dot, 0, 0, 1. So this is the binary representation of this number. And the reason why I chose this specific number is because it can be represented exactly in both decimal and binary, which is not the case for most numbers. Suppose, for example, I had instead chosen the number 1.1. So it's an exercise for the reader how precisely you can represent this number. In the particular binary representation called the IEEE standard for floating point arithmetic, IEEE 754, which was developed in the mid-1950s. Binary, and it uses 53 bits for the mantissa, including 1 for the sign, and it uses 11 bits for the exponent. The number can be written in the form some number equals minus 1 to the sign bit times 1 plus the sum on I equals 1 to 52 of b minus I 2 to the minus I times 2 to the e minus 1023. Okay, so first of all, let's look at the mantissa here. This is the type of binary number that I described on the last page. So the smallest increment compared to 1 that you could have would be b minus subscript minus 52, were equal to 1, and all the others would equal to 0, and that would give you 2 to the minus 52. If you wanted to add a number to the number 1, the smallest number that you could add to 1, or the next number up from 1, would be 2 to the minus 52. Okay? And now let's look at the exponent. And the exponent, e, runs from 1 to 2046. And there's 2 values reserved for special cases. Okay, now let's look at the implications of floating point. And to do that, it would actually be more convenient to go directly to MATLAB. So first of all, smallest possible floating point number that you can represent is 2.2251 times 10 to the minus 308. And the largest possible floating point number that you can represent is 1.7977 times 10 to the 308, and that's called real max. And then finally, there's a concept of machine epsilon, which in MATLAB is called EPS. EPS is the smallest number. So if you remember, I said that the next number up from 1 is 1 plus 2 to the minus 52. So 2 to the minus 52 is actually equal to EPS. So that's not quite the same as the smallest number that you can add to 1 to get a number that's different than 1, because of the fact that when you do addition, you round up. I'd also like to mention before we leave this page that MATLAB has a very helpful function called epsilon of as a function of some number. And so if I type help EPS, I learn that the function EPS of x is the positive distance from some number to the next larger in magnitude floating point number. We generically use double precision, not single precision. The double precision binary floating point format is the one that I described on the previous page. Okay, if we go back to our notes, the smallest number that can be represented, a largest number that can be represented, a finite number of numbers that can be represented, which means that there's some spacing between numbers whose absolute magnitude depends on how large the number is that you're looking at, and that is usually called machine epsilon. The final thing that I want to mention before we close this lecture is the fact that the difference between a number and its representation in the computer is called round-off error. And that'll be the topic of our next unit, which is on errors.